Thank you. Yes, I'm going to tell you how we at Nox Medical use artificial intelligence to detect sleep stages. So first of all, Nox Medical is a company in the health industry. It was founded in 2006, and we develop both software and hardware for diagnosing sleep. So our mission is to improve general health by improving sleep diagnostics. We want to make it more simple, more efficient, and more comfortable. And so if you or your child are experiencing some symptoms of poor sleep, you would consult with your doctor, and he or she would set you up with one of our devices. You'd go home and sleep one night with it, and afterwards a sleep technician would review the recording and diagnose any sleep disorders you might have. And currently there are 12,000 Nox devices in use around the world, and thus we can estimate that around 1 million people are being tested annually. On the picture here you can see one of our devices called the A1, and it's recording various biological parameters, brainwave signals, respiration, and position of the patient. And here you can see a sleep technician reviewing a recording from this device. So she's evaluating each 30-second interval of the recording, and she's assigning a sleep stage to every interval. And if we take an 8-hour measurement, this means that she has to do this around 1,000 times, which is very time-consuming. So our role with this task is to previously automatically assign a sleep stage to each interval, and subsequently she only has to review those sleep stages instead of starting from scratch. Now she's working with a complex set of non-deterministic rules specified, for example, by the American Academy of Sleep Medicine. And they're so complex that on average we can expect two sleep technicians to agree in maybe 77% cases of a sleep stage. So why so complex? It's a rather traditional trait. The method was standardized in 1968, and it hasn't been changed much since then. So it's a system designed under constraints from this machine over there, who records, or rather writes down brainwave signals from a patient hooked up to the machine, sleeping, and writes them directly on a piece of paper, which fits 30 seconds of signals. And the sleep stages were created initially by specialists who took these pieces of paper and categorized them based on their similarities and differences, and in relation to the current state of the patient, they decided on a sleep stage for each pile, basically. And this was obviously done using their eyes and not computers. So as a result, today we are still stuck with this 30-second interval, and in this lecture I'll refer to this as an epoch. And furthermore, we're also stuck with the sleep stages and their rather floating definitions. So now we expect that a computer should be able to do the same. That is, tell this from this and this, all different sleep stages. So, more details about the sleep stages. If we include wake, there are 5 of them. That's REM, or rapid eye movement sleep, which is probably the most famous sleep stage. And then non-REM sleep stages, labeled 1, 2, and 3, 3 being deep sleep. And these charts show you the average sleep cycle overnight for a healthy person. So a little time spent in all of them. The first 2 cycles end in sometimes spent in deep sleep, but as you get near through the morning, you spend more time in REM. And still today we use the brainwave signals to detect the sleep stages, like in the old days, but today we also use eye and muscle electrical activity signals, as well as a position signal to detect if the patient is moving or not. So, again to the epochs. This is the same screenshot as we saw earlier. This is from our software Nocturnal. And here you can see the topmost signal is the position signal. Then we have the 2 eye signals, one for left and one for right eye. Then we have 6 brainwave signals of the patient, which is actually me. This was done during a validation procedure at Nox. And here this fuzzy signal is my chin muscle electrical activity signal. So here I am still awake. And you can tell because my eyes are moving. That's the large waves in the eye signal. Brain signal shows high frequency, and there's also high activity in my chin muscle, telling us that the skeletal muscles of the body are active. Okay, the next stage that we go into when falling asleep is sleep stage 1. And here you can still interpret sounds, but you feel unwilling rather than unable to respond to them. I might twitch a bit in this state, and my brainwave frequency has become a bit lower, but otherwise this can be hard to distinguish from relaxation. Then moving on to sleep stage 2. It's a bit deeper sleep. So here I'm not able to interpret any sounds, and I'm gradually becoming unaware of myself. And for sleep state detection, this stage is actually a personal favorite of mine. It has 2 unique events that identify it. One is the sleep spindle, which is a high frequency event in the brain signals, lasting for around half a second. And then the K complex here in blue, which is a negative peak in the brainwave signal, followed with a high positive one and another negative. The brainwave frequency is lower still, and becomes even lower here in deep sleep. So here I'm completely out, and if somebody woke me at this point, I'd be disoriented for a while. And this is the sleep stage where the body repairs itself after the day. So it's vital that we spend some time here. And here you can see that the brainwaves are much slower than in the other sleep stages. So we dream a bit in all the sleep stages, but in the other sleep stages, I might just be flying over my hometown. But in the REM sleep stage, we have more vivid dreams. So I might murder a loved one by accident. More difficult stuff. And as for signals goes, this is actually very similar to wake. My eyes are also moving, and my brain waves have high frequency. But the difference is that my chin muscle signal shows low activity. And this is because the nervous system effectively paralyzes the skeletal muscles of the body during this stage for safety, which is necessary. And so we can tell those 2 apart that way. Now these are easy examples of sleep stages, and they are often more hard to distinguish than this. Some events are also seen in other sleep stages, just not as much, and it also differs from person to person. So moving on to the solution. It was a collaboration between 2 departments at Nox, the research team and the software team. At the research team, Sveinn Pálsson in particular developed a prototype of the solution. And in the research team, we have strong biological knowledge of sleep, and some signal processing expertise, both vital for prototype development such as this. And then us in the software team, me in particular, had the pleasure of implementing this into a product. And in the software team, we have a different viewpoint. That's what standards a product must meet. So there we're looking at processing power, execution time, and robustness in general. So why did we go with machine learning? To be honest, it wasn't a very hard choice. A lot about this problem screams out supervised classification problem. And those who are not familiar with machine learning, that's just one type of problem that machine learning is often applied to. It's well suited. So it's called supervised because the model that we're training, it is trained using labeled data. And we have access to this kind of data. It's recordings that sleep technicians have already scored with sleep stages for us. And it's called classification because in the same way as these cucumbers here have been assigned a class judging on their size and shape, we want to assign a class to the epochs. We want to assign sleep stages to them, judging from not size and shape, but some other useful features. And last but not least, since it's a set of non-deterministic rules, it will be very hard to program by hand. All right, we want a model that we can feed information about our epoch, our 30-second interval, and in return we expect an answer to the question, what sleep stage is most likely that this is? So the steps to achieve this by using supervised learning is that we first have to decide on and gather a good training set. Then we want to extract some features that best distinguish the sleep stages from each other. We have to choose a model and its internal architecture or hyperparameters. And then we need to train the model before we then, of course, test if it's good enough. So the training set must be at least as diverse as the cases it will be up against. And then in our case, this means that we want specimens of all age groups, and we want healthy patients as well as people with various illnesses. And we want samples from the whole night, because we want the model to be trained in all sleep stages. And the general rule is the bigger the better. So we first tried training a model with a data set that turns out consisted mainly of people suffering from sleep apnea, or kæfisvefn in Icelandic. And sleep apnea, if you're suffering from sleep apnea, your brain very often wakes you up during the night to allow you to catch your breath. And as a result, you spend very little time in sleep stage 3 or REM sleep. So your sleep stage distribution looks like the lower pie chart here. So our model had very little training in REM or deep sleep and just wanted to assign N2 to everything. But we were fortunate enough to have access to another data set. We got 169 recordings from the University Hospital in Iceland, which amounts to around 150,000 epochs. It was scored by 4 different sleep technicians and done very carefully, which is vital because all the knowledge the model will possess after the training comes from the training data. And we divided it 60% for training and 20% for cross-validation, which is also used during the training process, and then 20% for testing for ourselves. Then we needed to decide on a feature set that best accentuates the differences between them. For this, we used both internal knowledge of sleep from within the company, but also results from scientific studies. And we came up with 126 different features that we want to extract from the 30 seconds of data. Examples are frequency parameters, correlations between the eye signals and a thresholding of the activity signal, the position signal. Now we don't want to miss out on precious information and information about the sleep spindle and K-complex, for example, which last for a lot shorter than 30 seconds. So we first processed all the data in 2 seconds interval, but then we want to end up with values that describe the whole 30 seconds. So we had to transform these values carefully without losing this information about the short events. The last thing we want to do is normalize our feature values, because we don't want different scales of features to influence the importance regarding the model. During a selection of what type of model to use, our research team used a machine learning Python library called scikit-learn, which is very good for quickly trying out numerous machine learning algorithms to see which one gives best results. They tried, for example, support vector machines and decision trees before landing with an artificial neural network. And they work best because they're very good at capturing complicated patterns and input features. What gave best results was the recurrent neural network, which uses the last class you assigned to evaluate the current class. So you're not only focusing on your epoch, but also thinking if the patient was asleep in sleep stage 1 or awake before. So it fit very well to our problem, but actually we ended with using feed-forward, the regular kind of neural networks, because they gave almost as good a result, but were much easier to implement. That's sometimes how it goes. So for further development of the neural network model, we used Keras, which is a high-level neural network development library. But it runs on top of either Theano or Google's TensorFlow deep learning libraries. We used Theano, and we're happy with that. And this is an example of the model. So just for context, this here within the box is what is static within your code. And during execution, we extract feature values from an epoch. We send those 126 values into the input layer, and the values travel through different layers of the model, and they're multiplied with the weight of each connection between the nodes as they go. And in the end, they reach the output layer, which has 5 nodes, where each of them tells us the probability of each sleep stage. The internal layers of the model are called hidden layers, and the number of hidden layers and the number of the nodes inside the hidden layers is up to the designer of the model to decide on. But the weights is what gets assigned during the training process. So let's have a closer look on the training example. So before I said we need to decide on a model and its internal architecture, and then we train the model. But in the case of neural networks, these 2 steps are actually intertwined, because the neural networks are a bit of a black box. So selecting hyperparameters is a trial and error process. It goes something like this. We select initial hyperparameters and train the model. If it meets the pass criteria, we train it a few more times to make sure we weren't just lucky with our initial weights, which are then adjusted during the training process. If it's consistently good, we're happy and the prototype is ready. But if not, we select a new set and have to start over. And this is what I believe took the research team the most time during the development, because each training is very computationally heavy and takes a lot of time. So when they started using Amazon Web Services, the process was sped up considerably, so we recommend using that from the start if you're planning to train a model. The selection of hyperparameters can also be automated, but this is also rather complex. You can, for example, use another machine learning algorithm to do this. Now, once the prototype is ready, we want to implement it into our software. And both the feature calculations and the model itself are developed and written in Python. But our software is all written in the .NET framework in C#. So we thought about some ways that we could prevent ourselves from reinventing the wheel. But after some consideration, we found that there are so many additional requirements that are added once we want to turn it into a product that Python code would have needed a complete overhaul anyway. So in the case of the feature calculations, we actually did rewrite the whole thing. So some of these requirements are, for example, processing time. The feature calculations, in our case at least, were the most computationally heavy part of the whole sleep stage detection, so this is important in this step. We had to include various exception handling. We also have to assume that some sensor can fall off the patient during the night, so we have to be able to work without some input signals or gaps in them. We have to include a fallback plan. What if something goes wrong and we don't get the sleep stage assigned to an epoch? Do we leave it empty, or do we default to wake, for example? And we also want the maintenance of the code to be left with the software team and not the research team. They have to be free to continue researching. As for the model prediction goes, we were able to use an open source C++ project to read the model and use it during the detection, and wrap that all up in a C# class, which we could sufficiently error-proof. And the maintenance of the model, which is basically retraining of a model, would anyway be left with the research team. So we were happy not having to rewrite the neural network model completely. And then, of course, we'd like our code to be as unit-tested as possible. So we want both to include tests that make sure that it behaves exactly like the prototype, but also include any side cases that we could think of. The final product was tested on 28 recordings, or 25,000 epochs. And on average, our automatic scorer agreed with the manual scorings in 78% cases. And as you maybe recall from the beginning, this is very similar to what you can expect between two human scorers. So we were happy with this result. A bit further analysis. This matrix there shows the level of agreement between the manual and automatic scorings per sleep stage. And you can see that for sleep stages 2, 3, and REM, which make up for the largest part of the night, the automatic scorer gets over 80% correct answers, or same as the manual scorings. However, it does not score sleep stage 1 very accurately, which is also an interesting conclusion to me, because this is also an error. This is also a difficult task for human scorers. And also, we spend very little time in this sleep stage during the night, so the model is just less trained in sleep stage 1 than the other ones. And then I'm ready if you have any questions for me.
Yes, thank you. Thank you very much. Are there any questions in the audience? Okay, there's one. Could you please repeat the question?
Yes, he's asking if I could mention what type of recurrent neural networks we used. Fortunately, it was a bit of outside of my scope, but I could set you up with the guy from the research team who did try these out. But they made perfect sense to use, the recurrent neural networks, because of the nature of our problem. But to compensate for using the feed-forward networks instead, we used another algorithm that was outside the scope of this lecture. We used a Viterbi algorithm, or a Markov model, to take the results from the model in total, all the epochs, and sort of change the probability for each epoch, judging from the states before.
Another question from the audience? If not, I thank Nanna very much for an interesting presentation. And we will start again here in 10:40 with Alma Tryggvadóttir from Persónuvernd, but she will talk in Icelandic for our English audience. Thank you very much.
Thank you.